Okay, let me begin. This is based on some work I've been doing recently with people here, people in ICTS, as well as Shota Komatsu, Edward Mazenk at ETH, and Dave Malya at Harvard, and also based on earlier work and fleshing out ideas I have been trying to think about for quite some time. So this might seem a little unfamiliar, but I saw that the location of Bimsa has at least a nice illustration of some of the points. This is the hotel that maybe some of you are at, the Kempinski down here you might have seen. But anyway, it will make an appearance in the talk. So which is it? This one? Yeah. So let me first just give a one picture summary if you want to take something away. So this is the carry away picture. We are all familiar with the idea of open-close string dualities or gate string dualities, whatever you call it, in which there's a sort of a closed string theory, and there's a gates theory dual to it, and you have some picture from Toft of the gates theory ribbon diagrams becoming the closed string theory. But one of the main things I want to actually convey is there's a kind of a refinement, a very interesting refinement of this picture of gauge string duality, which at least is more manifest in the perturbative limit, in which there are two kinds of open strings, two very dual open string descriptions, which I'll explain later. I'll call the vertex type and the face type. And so these are two different string theories or two different D-branes. And there's a kind of a very interesting triality between these three descriptions, which I'll try to flesh out in some simple examples, but I believe it is more general, which is one reason I'm speaking about it. And we'll see some evidence to that effect. So that's the carry away picture, as I said. And this is the plan of the talk. I'll first explain what this B type and F type kind of open closed string dualities are and illustrate it in a simple case, which actually Raghu very helpfully set out, the case of a single matrix model, in which there's also another matrix model, the Kontsevich matrix model, and these will play the role of these two different open string descriptions. And then I'll try to explain why the relation between these two different open string descriptions is a kind of a dynamical graph duality, which kind of operates at the level of the Feynman diagrams and has a very physical meaning in terms of multiple D-brane pictures, different D-brane descriptions. I'll also then try to, building on that, sort of explain how this triality fits very well with a certain proposal for constructing world sheets from these Feynman diagrams through a very interesting parametrization of the moduli space coming from these mathematical construction of Strebel. And then finally talk a little bit about how you to go to something like n equals to 4 super-Yang-Mills and what this triality might mean in that case. This would be very preliminary, very kind of baby steps there, but I believe there's a bigger picture to be uncovered, and I'll just conclude. Okay, so let me explain this sort of two dualities, but firstly, gate string duality, as we all know, arises essentially, I mean, the reason Maldacena came up with this was that there are two pictures of D-branes we carry in our head. One is in terms of open strings, which some limit become gauge theories, but we can also view D-branes as solitons in string theory, the objects which kind of back-react create a certain geometry, and it was demanding that these are consistent descriptions that led Maldacena to propose the correspondence in the first place, that these gauge theories and these near-horizon geometries must be just dual descriptions of each other. And as we know, this has been very powerful in both gauge theories and in quantum gravity. We'll focus on a regime which is a perturbative regime, which is where we understand the field theories or the gauge theories best. That's the regime where the coupling is much less than 1. In terms of the string theory, in terms of the usual dictionary between the bulk and the boundary theories, this corresponds to a highly curved geometry or a near tensionless limit of the string theory. So it's a regime we all study in our QFT courses in gauge theories, but it's a very unfamiliar regime from the point of view of the string theory, being a highly curved geometry. But in that regime, the gauge theory is described by simple Feynman diagrams. And then somehow these Feynman diagrams must sum up to give these closed string amplitudes. And that's what this cartoon kind of is, some kind of an inverse Cheshire cat cartoon, which kind of exemplifies this. But this regime is a very tractable one because we understand at least one side very well, the gauge theory, and we can try to kind of build this and try to connect with the dual string theory. And in the case of ADS3 CFT2 with Never-Schwarz flux, this was actually realized a few years ago in work with Matthias and Lawrence Eberhard. So it's a tractable limit, and I'll focus therefore on this perturbative limit where we understand this Feynman diagram picture. And that's where I want to kind of draw your attention to a refinement of the usual open-closed string duality that we talk about, and make this distinction between sort of the vertex type and the face type dualities. In some ways, probably the space type is not something very familiar to most people. The vertex type is what we normally think of. And what is that? I mean, that's in the examples I will mostly talk about are, say, the usual ADS CFT with, say, n equals to 4 super Yang-Mills, or the case which appeared in Raghu's talk, double-scaled matrix models or regular matrix models. The salient feature in all these that I want to point out is that we consider an endpoint function of the gauge theory, some endpoint gauge theory correlator, and that's dual to an endpoint string amplitude. So it's the same. So in a sense, these vertices, or these external vertices of the Feynman diagrams, become the closed string insertions on the dual side. So that's why I call it a V-type. In some sense, the vertices of the Feynman diagram, or at least the external vertices, you can think of the internal vertices also in perturbations, but I won't dwell on that right now. But roughly the picture is that it's the endpoint gauge theory correlator that becomes the endpoint string amplitude. But this is not how actually all these open-closed string dualities operate. There is a kind of a complementary way in which the open-closed duality operates, which is also very natural physically. And in fact, sometimes we confuse the two because we actually confuse the two because but they are actually distinct, because in this picture we can there are dualities in which the faces of the Feynman diagrams correspond to the closed string insertions as opposed to the vertices. And why is that natural? That's because we can also think of these faces of the Feynman diagrams as boundary states. I mean, these as boundary states of D-branes, and in some sense, has been this picture of that the D-brane boundary states in some limit become essentially the closed string, the closed string insertions. And so this is what I've illustrated here, where you have some free energy diagram which has 5 faces, and that corresponds to essentially, you should yeah, maybe it'll become clearer in other diagrams, should think of each of these faces, the boundaries, as sort of shrinking and becoming these string insertions. So this is one in which the faces really are dual to string insertions, and that arises from this other picture of D-brane boundary states. Any questions about this? So I'll flesh this out. And this is the way in which it actually operates in a few examples of dualities like the Chern-Simons duality, or even earlier the Conserich matrix model, and now a few other cases that we know. It's a less familiar kind of a way in which open-closed string duality plays out, but I think, and we'll try to flesh out the relation between these different pictures and the dual closed string. So that's the sort of the goal, to sort of have this triality where you have these two open string descriptions, V type and F type. But one of the stronger statements I want to put out there, for which there's some evidence, is that there's always two different pictures. I gave you cases, I mentioned some cases where you have this vertex type or face type, but what I want to say is that there are always two different open string descriptions. And in one, the open closed string duality is realized through this vertex type, and the other one, it's realized through the face type. And the Feynman diagrams of these are actually graph duals of each other. That's what interchanges vertices and faces. So, so that's what I'll try to flesh out. Firstly, through minimal string theory, which is actually an early example of how this. It wasn't phrased in this way, but it will turn out to be a realization of this triality where you have all the three elements of this, and that is something which one can be very explicit about. And in that case, these two different descriptions will turn out to be two different D branes, which maybe many of you are familiar. The ZZ branes appeared in the previous talk. There are also these FZZT branes, but roughly speaking, these two open string descriptions are associated with these two different D brane pictures. Okay. Yeah, please stop me if there are any questions or anything you would like to think. Yeah. Sorry. So the loops, you mean the Feynman loops? Yeah. Yes. Correct. Yeah, that's in this picture. So what is the question? Yes. In the in these in oops. This thing. Yeah, it's just that you can think of the gauge theory has these Feynman diagrams, and you should think of the D-brane boundary states that create these Feynman diagrams, and the back reaction, which gives you the closed string, is coming from the sum over all these faces. So you normally think of the original D-brane in some background, and then when you sum over all these Feynman diagrams of these faces, you get the closed string in a dual background. So in a sense, what you have in mind, yes, in general, if I consider all loops, I have multiple insertions, which will exponentiate in some sense to deform the background, which is why you start with a closed string D-branes in some flat space, let's say, and you go to near horizon, or in this Chern-Simons case, you start with the deformed conifold and you go to the resolved conifold. So that's what the loops do. They the closed string insertions are essentially exponentiating to deform the background. Yeah, yeah. So this is all in the context of a large light expansion, where you have where you have fields, matrix valued fields of some kind, and you can assign a genus, you can assign these things. Yes, you need to have a sort of a graph on a Riemann surface. Uh, Okay, so I'll illustrate this with a very simple example, which I can almost take you through all the steps. So this is, as I said, in the minimal string theory, which there are two pictures. There's the double scale matrix model, which entered in the previous talk, in terms of some n by n matrices with some potential, which I won't actually, the double scaling will be actually not so relevant for this thing. What I'll have to say will be true independent of double scaling, but this is how it originally appeared. So I'll phrase it in that context. So in the double scaling limit, as you saw in the previous talk, you have a potential and you have to scale the parameters in some appropriate way, and you get a closed string. It's dual to some closed string background, which are these minimal model theories coupled to Liouville. Famously, Kontsevich also showed that there's another matrix model, at first sight unrelated to this, in terms of, so I'll denote this Hermitian matrix model with n by n matrix. This is the q by q matrix, and this is a cubic matrix model, which has which has a kinetic term and this sort of cubic term here. And this looks at first sight very different from these, but the idea, and this is how Kontsevich established Witten's conjecture, that this matrix model generates the intersection numbers and moduli space, which is what this closed string theory really computes, same as what this double scale matrix model does. So as I said, and Raghu mentioned, that the idea then was that you need this double scaling for taking a continuum limit, but actually the double scaling limit is not strictly speaking needed. You can still define a string theory even without double scaling. So I will, the double scaling is just a prop for the moment. But let me point out a couple of features in this. I will actually try to tell you how we can go directly from here to here. You notice that the sources here, these TKs, are the sources that parameterize the potential, of course, but they also parameterize they are related to the closed string background. So the sources appear linearly. This is why this is a V-type duality, because you want to compute an endpoint function, you differentiate with respect to t, and you pull down those observables here. So you get a gauge invariant correlator of these. An endpoint function of these is related to an endpoint function of the closed string. Whereas the sources t, which in this appear in a very kind of a hidden way in this matrix X, which is a fixed matrix, a background matrix, and it's related through these sort of Miwa times, these traces of this matrix. So you see that so it's not appearing linearly. The sources are not appearing linearly, and in fact, a Kontsevich derivation needs the fact that it's each face which is related to the closed string insertions, and that's what this matrix model really generates. And these give you these psi classes. There's you can also work on this side without the double scaling limit if you don't do it over here. And this Kontsevich used this particular parameterization of moduli space, which I will talk about soon. So this is a case which I will now explain in a little more detail how these three pictures, this open, and closed pictures, are related. So So it basically follows from some kind of a matrix identity. And this was established essentially in these papers. It's a straightforward identity, as I'll show you, which basically takes sort of a correlator of determinants of this form in a Gaussian model. And the claim is that this correlator, or this matrix integral, is the same as this other matrix integral, and this matrix X is the same matrix that appeared earlier, and but it's just a diagonal matrix. It's a fixed matrix with some numbers XA. So think of these XAs as basically parameterizing those sources Tk that I showed you earlier. So in fact, this left-hand side of this identity, which I'll just establish, this left-hand side can be also rewritten as a sum over traces of polynomial sum of these traces of the basic matrix M with these sources Tk related, like I said before. So this, if you wish, is a generating function of correlators in a Gaussian matrix model. That's essentially what the left-hand side of the minimal string theory in the V-type was. It's just a one matrix model, and you're evaluating general correlators of this kind. And the claim is that this is related to this other theory, which has this q by q, this parameter q, and the n, which was appearing here, is just an overall term here. So you see that n really plays the role of 1 over h bar in this. N appears nowhere else in this on this side except as this overall scale, whereas here it's an n by n matrix, everything appears. And q, on the other hand, here appears as basically the number of these determinant operators. That's the same q over here. So that's how the n and the q are related in this sort of very interesting way. And this identity is what once one does the double scaling, the left-hand side becomes the double scaling theory, and the right-hand side becomes the Kontsevich matrix model. But that double scaling won't be really essential. The matrix identity is all I need. So the matrix identity, yeah, it fits in on one slide. It's basically, I take this determinant operators and write them in terms of fermions. So I integrate in a certain number of fermions, which are in the bifundamental, because there were q of these. So I have this matrix X, which is sort of a diagonal q by q matrix. I can basically, this is the determinant of X minus M, which if I were to integrate out size, I would get back what I had earlier. So I'm integrating in some bifundamental. So I and J will refer to the n by n labels, A and B will refer to the q by q labels. So it's the Hubbard-Stratonovich kind of transformation in which you then integrate. Now, unlike before, this is just a Gaussian integral in M, which you can carry out, and you get something involving a quartic term in these fermions. And you can integrate in now another matrix, now a q by q matrix, and you can rewrite it this way, and then you integrate out the size, and then you get this. So it's very straightforward. Even if you don't follow all the details, at least you should have the conviction that this is something straightforward to carry out. It's just integrating in and integrating out. So that is what is behind this identity. And so it looks like a mathematical trick, but it has, I think, a lot of meaning. And that's what I will try to sort of extract out. So firstly, yeah, so as no, a priori, no. But if you want to explore the whole phase space of the p comma q, the 2 comma p minimal models, you need to take q also very large so that you can have arbitrary parameters tk. But yeah, but a priori they are independent. This identity, in a sense, holds for finite n and finite q. So what I want to say is that this identity essentially follows, is a realization of a graph duality. So what do I mean by that? So let's just go over each of the steps, and I'll just tell you what the corresponding picture is. So each of the steps has a pictorial analog. So integrating in fermions. So supposing I start with this. So as I said, this is basically, so the dark, I mean the, what is it called? The solid lines are the indices for the n by n matrix M, and this is just behavior near some vertex. So remember, I wrote these. You could also view these determinants as basically generating function of these trace m to the k. So you can have vertices of various valency. I've just taken one here. And what does integrating in the fermions mean? It means sort of blowing up this vertex into a little loop involving these fermions. The fermions are in the bifundamental, and that's the dotted lines are signifying the other index, the Q, the AB indices. And you now have these fermions which are propagating, and you have cubic vertices between the bosons, that are the M's, and the fermions. So you have a sort of a psi dagger, psi and M vertex, and then you have fermion propagators. So that's what this integrating in psi and psi dagger does. Now, when you integrate out the so the next step, remember, was integrate. There's a Gaussian integral. You integrate out the matrix M. Integrating that out basically means collapsing these M propagators, which are the Gaussian pieces, into a quartic vertex for these fermions. So this is the Yukawa coupling between the two fermions and the matrix, and you basically collapse it into a quartic vertex. That's what happens when you integrate out this field, this propagator over here. And now the next step was to integrate in a different field, now the Q by Q field, and you can see that that's the thing that kind of is this Whitehead move, which it goes from this to collapse to this, but then now expands it out in this dashed line, which is the B propagator over here. And then finally, when you kind of look at the behavior near any of these vertices and integrate out the fermions, you get something which is purely in terms of these dashed lines, which are the vertices for the B field. Now, so in this whole process, what you have done is to go from the graph to its dual, essentially because you have, and this is the key step where you can see that you go from each edge to a transverse edge, and then you replace the faces by vertices in the dual picture. So this Hubbard-Stratinovich essentially implements this graph duality. It's a very, in fact, I once had a movie which I've lost this file. You can actually try to see each step, and it's very beautiful how the vertices open up and then one graph transforms dynamically into the dual graph. I wish I had that movie to play, but anyway. And there's also a physical meaning to this. So this is a kind of the graph theoretic meaning, but there's a physical meaning, which is that we started with one set of open string states, n by n matrices, so n d-branes of one kind, and we had a background created by these determinant operators. There were q of them, and which you can view as sort of a different set of d-branes, and there are q of those. And these bifundamental fermions are transforming in the n comma q, and they can be viewed as the open strings between these two different sets of d-branes. And what we did was then we integrated out the original set of fields here, and we integrated in the degrees of freedom of the second set of D branes, and we integrated out the fermions, the bifundamentals, and you got a second open string description purely in terms of the dual set of branes, these ones which have the determinant operators. And in the minimal string theory, these are the ZZ branes. This was the interpretation in the mid-2000s about the matrix models being related to the open strings of the ZZ branes. And the interpretation by Gaiotto and Rastelli that the Kontsevich matrix model is the open string field theory of the FZZT branes. And what we have now also learned is that the corresponding open string diagrams are graph dual, and this is what exchanges the V and F type descriptions. So you have, this is why the Kontsevich description is a sort of a one which is phase type, whereas the double scale matrix model is a sort of a V type description. Okay, any questions before I move to the sort of the second part of this? Okay, so now what, so this I illustrated in this simple example, how these three pictures exist. And now I want to make it also, in a way, what makes it more compelling for me is that this fits in very naturally with a way in which you can build the closed string theories from the open string theories. There's a very natural mathematical construction to build the closed strings from the open strings, and which realizes both these sort of V-type and the F-type kind of pictures, I think, in a unified framework. So that's what the next part of the talk I want to focus on. So these two open string descriptions, so far what I at least illustrated in the simple example was that there are these two different types of open string descriptions which correspond to different D branes. And this, I now want to say, fits beautifully with the corresponding closed strings and builds on this proposal to associate a closed string worldsheet to each Feynman graph of the dual open string theory. Now, this is not how you conventionally think of open closed string duality. You don't, you think of somehow the open string theory as all these Feynman graphs and they add up and they give you the closed string amplitude. I want to make a stronger statement here, again, borne out by many of these cases, that you can actually associate to each Feynman graph, at least in a special gauge, you can associate a closed string worldsheet, and this the way the corresponding gauge, if you wish, is one which uses a certain parametrization of the moduli space of the Riemann surfaces, genus G Riemann surfaces with n punctures. It's a very physical way, which I think should be better known among physicists. And I'll try to sketch that very briefly. I don't have the time to explain it in detail. I think I've done that in the string math talk recently, for instance. But the key element of this construction is the existence of, on any Riemann surface, the existence of a very special, and actually under certain conditions, uniqueness of a very special meromorphic quadratic differential, which is called the Strebel differential. So what is this Strebel differential? As I said, it's a quadratic differential, but the nice thing about it is that it has a few very key properties. It has only double poles, so this meromorphic phi of z d z square has only double poles. It has, and now if you talk of for any quadratic differential, you can actually define a very interesting notion of what are called the horizontal trajectories, which are essentially the curves on the Riemann surface, z of t, where this condition is satisfied. And if this is a little mysterious, that's the terminology is basically coming from in the complex plane. if I just consider the dz square, just the canonical dz square, then the horizontal trajectories are really all these horizontal lines, as you can just convince yourself. So locally, of course, you can always make meromorphic differential in this form. So locally, you do have a behavior which is like this, but near a double pole, it's different, and that's why the behavior near a double pole is really like a set of concentric circles, and you have so you can imagine, and it's easy to convince yourself that near when phi is like 1 over z square, the behavior are essentially these concentric circles, but as these circles grow out, they kind of collide with each other, and you form these so-called critical horizontal trajectories, which is sort of where these different things collide, which forms a graph. And I'll call that, it's I think conventionally called the Strebel graph. So the particular nice thing about the Strebel differential is that almost all the horizontal trajectories are closed curves, except for these sort of this measure zero kind of set of trajectories, which is a graph. And the nice thing about this graph is that each face of this graph has exactly one double pole, and the vertices of this graph correspond to the zeros of the Strebel differential, and the valence of a vertex is basically the order of the 0 plus 2, which is the plus 2 is essentially because it's a quadratic differential, and it's easy to see that near a generic zero, a simple zero, it's cubic. The order of the zero is 1, so this is a cubic vertex. So the generic vertices of this graph are cubic, but of course there can be special cases where you have a double zero and then it'll be quartic and so on. But generically, this is the structure, and this I've drawn it for genus 0 for 4-point function, but this is true more generally. This is the result established by Strebel, that on any genus G Riemann surface with n punctures, you have this unique differential. Well, you have to specify the residues at these poles, and then it's a unique differential, and you have a graph in which there are exactly n faces. The faces of the graph each contain a double pole. So if I have an n-point genus G with n punctures, I basically will have n faces in the corresponding Strebel graph. So this is the picture, and this is why, thanks to Wei and Matthias, you see that there are these very nice horizontal trajectories that the hotel has very kindly illuminated for us. So I suspect there's some grand order in the universe. So anyhow, the Strebel actually used these, and I won't directly use them right now, but I just wanted to mention that Strebel used this existence of these special differentials to give a parametrization of the moduli space, and it's parametrized in terms of the lengths of the edges of these graphs. There's a theorem that if once you specify the residues of these n poles, then basically the edges of these graphs and together with the topologies of the graph basically cover the whole moduli space exactly once. I mean, and this was, as I said, alluded earlier, was exploited by Kontsevich in his proof of the Witten conjecture. So that's something. So what I now want to say is that this picture is that the Strebel graph is really at the heart of the F-type duality. So the Strebel graph, remember, as I said, has faces which are associated to the punctures, or the equivalently the closed string insertions, and it's therefore natural to associate it with the graphs of the F-type dual, and in fact in the Kontsevich model is exactly what happens, and similarly with some of the other models of this type, This is a matrix model, the Chern-Simons theory. And the picture is that these critical horizontal trajectories correspond to the edges, and the zeros are these, remember, these were the zeros. The vertices of this treble graph are the zeros of the treble differential. These correspond to the vertices, and there are edges which correspond to those critical horizontal trajectories. And the generic vertices are cubic. And this is very much like an open string field theory. So the open string field theory picture in fact, the D-brane boundary state picture is itself an open string field theory like picture. So this is, if you wish, the open string description coming in, which is inherited most naturally from an open string field theory. We don't normally think of ADS-CFT in terms of the open string field theory because it's not cubic theory, but the Chern-Simons theories, the Kontsevich model, all these very naturally inherit. They're kind of simplified open string field theories, and that's why they have a slightly, and this is the difference between that and the conventional F-type duals, the B-type duals of ADS-CFT, that these are kind of, the Feynman graphs here are related to these treble graph directly with this sort of this identification, and the moduli space emerges when you sort of sum over all the Feynman graphs just using this treble parametrization. So this graph is at the so this is a picture, if you wish, of how you would build the Riemann surface in this F-type dual. So basically, each of these faces is a disk with a puncture, which is conformally equivalent to a semi-infinite cylinder like this. And so this picture is really one in which I'm replacing these sort of boundary states by these closed string, this closed string insertions. And so if you really look at the Kontsevich derivation, for instance, this is essentially how the corresponding, how he builds up the closed string insertions, namely the psi classes. So this is the picture behind it in some sense. But I think this is a more general picture valid for any F-type dual. But this treble differential, as I said at the beginning, the reason I'm talking about this is that because it unifies both the B and F type in a very natural way. The same treble parametrization can be also used to think of the V type graphs. And for that, you need a complementary notion, which also exists in the theory of quadratic differentials, the notion of vertical trajectory. So I defined the horizontal trajectories as ones where this phi dz square is positive. If you look at the cases where it's negative, you call those vertical trajectories for the same reason as in this, that the vertical trajectories, when you have dz square, are essentially these vertical lines. So you have along the imaginary axis, and that's why dz square you get to be negative. So you have these blue lines are basically the vertical trajectories, and you can again locally it will be transverse to the horizontal trajectories, but near these poles it's different. So unlike the earlier case where the horizontal trajectories were concentric circles, the vertical trajectories will be radial lines. Well, it's kind of natural. They're kind of the transverse to the earlier set, and they all emanate. So these vertical trajectories basically emanate from the poles. They begin at poles, end at poles, and you have structure like this. And in particular, you can focus on these so-called the special vertical trajectories that kind of join up a double pole with a zero of this treble differential, and you get a kind of a semi-infinite strip, or conformally equivalent to a semi-infinite strip. Or if you look at the whole thing coming from the other side, it's like an orange peel, and you get a full strip. And so what the vertical trajectories do is carve the Riemann surface. So once you're given a Strebel graph, the vertical trajectories help to carve the Riemann surface into infinite strips, which you can now identify. So these are, as I said, these are transverse to the edges. So this is very naturally gives rise to the graph, which is dual to the F-type graph, to the Strebel graph itself, because these vertical trajectories are transverse to the Strebel edges. And so you get the graph dual. The Strebel differential has, through these assignments of these horizontal and vertical trajectories, a very, so two complementary ways of kind of associating different graphs, the original Strebel graph, which is kind of cubic, and then this transverse graph, or the graph dual, to this, which is, as I said, coming from these special vertical trajectories. And so these are what you would associate to the V-type dual, because now you see that associated to each puncture is the poles of the quadratic differential are the vertices, and the valence is the number of faces of the corresponding Strebel graph. So each of these vertices, each of these poles will have some number of strips, or some number of these strips or dual edges emanating from them, which I think I've illustrated in this picture. So each of these strips is conformally equivalent. So you have this strip coming and meeting this, and then this is the bottom strip. So if you put these two together, that's the dual edge to this one, and you get a ribbon graph here. You get another. So on this edge of the Strebel transverse to this is this semi-infinite strip plus this, and you get another dual graph. So you see each of these strips are ending at the double pole. So the vertices of the graph of this graph are the punctures, or the insertions of the closed string. So the closed string is essentially assembled now from these strips, and so these are the ones that you would identify with the ribbon graphs of the dual, the V-type large N gauge theory. Yeah. Yeah. Oh. So if you specify the residues, then it's a one-to-one correspondence to a point on the moduli space of Riemann surfaces. But there's also a unique graph with a topology and with a length assignment to the lengths of the graph. So yes, so a graph with a length assignment to the edges of the graph. So that's a unique one-to-one correspondence, which is guaranteed by the theorem of Strebel. Yes, the double pole is crucial for this. Yeah. I don't know how to say it, but there's a slight generalization which is called the Jenkins-Strebel differentials. I think maybe some mathematicians here might know, which you allow single poles as well. But those, but for this construction, it's essential that this has only double poles. Yeah, that's a little bit subtle. I think some people have tried to extend to the Deligne-Mumford degenerate surfaces. I think it partially extends, but there is a subtlety, which is why I think even in the original Kontsevich proof, I think there is a small gap in that aspect, I believe. Yeah. Yes. No, that it just goes from one. I don't have that picture over here. So basically what the um, uh, what this treble parameterization gives you is a cell decomposition of the moduli space. And the top dimensional cell is when all the vertices are cubic. And so you have the maximal number of edges. And so you have some cell of the moduli space. And then there's a codimension one place where one of the lengths goes to 0, you go to a new cell. And that's like basically this graph again going to this, but going then to this. So you change the topology locally and you go to another cell. And then you keep doing this and you have all the graph topologies that gives you the full moduli space. That's part of this treble construction. Sorry, there was something else? Someone asked something? Could also dualize cell decomposition apart. No. This cell decomposition. Yeah, whether you attribute it to the graph or the dual graph. Yes, correct. So I kind of sketched for you this picture, which of course you can. I sketched more in pictures right now, but a lot of this you can see very explicitly in that simple model that I showed you. But you would like to. I wanted to claim that this is very much more general. It applies, I think, to any of the open-closed string dualities that you love. And in particular, I want to try to tell you at least some baby steps in the n equals to 4 super Yang mills, and maybe again flesh out a little bit more about what it means. I think it has a very interesting meaning also beyond the pretty mathematics of graph duality. And as I said, there's multiple D-brain interpretations. So this is, so you can actually, the context is a set of half supersymmetric correlators in n equals to 4 Yang mills, where you have where you can essentially reduce it now to a two matrix model. So again, we are reducing it, and as Raghu's tried to say, you want to try to reduce all the complications of the gauge fields and so on. And so, but this takes you one step beyond what we had earlier. Now you can consider two different sets of determinant operators, and these effectively because this correlator, if you choose the directions appropriately, it preserves half the supersymmetry. You can assign. You can think of these as two different matrices. So effectively, the Yang-Mills path integral reduces to a two-matrix integral with a simple kind of a kinetic term, a Km kind of a term, and then you have these two different sets of determinants. And you can see that these determinants are really arising from these giant graviton operators that are there in the n equals to 4 super Yang-Mills, which correspond to D-branes now inside the S3 of the ADS 5 times S5 and extended in some sort of the time or radial direction. So that's the underlying correlator you're considering. You're considering some correlator of giant gravitons. And in fact, this was studied in papers by Shota and collaborators, and in the context of twisted holography by Budzik and Gayoto. And this very interesting recent, not so recent paper by Karen Huo and collaborators, which also compute this in a way which I find suggestive, which I won't talk about, but you can look at if you are interested. But let me first just explain the statement here. So you have this correlator in n equals to 4 super Young mills, essentially reducing to a 2-matrix integral. And again, you can think of these as essentially sources for trace k to the n and trace m to the n. So the generating function, if you wish, of multi-trace correlators like this is reduces to that of a 2-matrix model. And you can do very similar things. It becomes more intricate, but now you have sort of, you can actually do many more, Sorry? Yeah, because essentially it's supersymmetric, so the correlators don't depend, or the dependence on the positions is very trivial because we've chosen these fields, in the S5 in a particular way that preserves supersymmetry. These two different fields, like Nadav and others have done before. So you can consider it's a simple class of correlators, but it's a subset of the n equals to 4. Sorry? No. The whole thing preserves half supersymmetry. It's not the individual ones. These are correlators that preserve, the whole correlator preserves a certain amount of supersymmetry. So it's not the individual ones. We can talk about it later. But yeah, no, I think these are exact. So, and you can argue that. So it's simple. So, but that's okay. These x's, these correspond to essentially the sizes of the brains and so on. Exactly, in the different. You're choosing some different. These y's are in the S3, x's are the radial size, and so on. I won't dwell on this in detail, but you can flesh it out over here. You get sort of so the V-type duality is the one we start with in n equals to 4 Young mills, which has these correlators of trace k to the n, trace m to the n. But then there are the open string. You can do the similar kind of a game, and you get sort of a more complicated. Yeah, 315. Yeah, I'm almost done too. So you started with strings on the ND3 brains, which was what the original ADS-CFT correspondence was from, but you're rewriting it in terms of strings on these giant graviton brains, the dual brains, and they're both related to this closed string ADS5 times S5, a set of correlators in that, and they have the same triality. So you can actually, again, the graph dual is more intricate, but you can again make a movie out of these by sort of once again opening out vertices, and now there are two different kinds of vertices. So it's not so trivial that it all works out, but you can do the same sort of Hubbard-Stratinovich sort of thing, and then you have to sort of wrap your head around these diagrams, and then you see that you end up with the dual graph once you do the same sort of steps of integrating in fermions, etc. So you need to kind of play this movie in your head to see how you go from the original graph here to the dual graph over here. And this is the process in which you go from the description in terms of the original D-branes to those in terms of the giant graviton D-branes, the dual set of D-branes. And that is why I claim this is more physical and relevant, because I think whenever there is a dual giant graviton description, I think that will give rise to an F-type duality, which is complementary to the original V-type duality, which was obtained from the near horizon geometry of D3 branes in flat space. But this F-type dual is more natural for starting from the giant gravitons in the tensionless limit of the ADS string theory. So these are giant gravitons in the ADS, and you're looking at the open string descriptions of those giant gravitons. And that it's this, I think that's what makes it interesting for me, that there are these two different brain perspectives. One which is sort of more natural from the strong coupling limit for D3 brains in flat space, to the other one which are starting from the D3 brains, but a different set of D3 brains in the curved spacetime of the tensionless ADS. So just a few remarks. So these F-type duals, which are sort of the more unusual ones for perhaps most of you. So I just want to say a few last comments on these, that these F-type open string duals are probably more natural from the tensionless limit. As I'm saying, perhaps understanding the enhanced symmetries. And in some ways, I feel it gives a more direct handle on the emergence of the bulk, because they are really, in some ways, they know about the ADS. I think there's been a reflection of this, and in the work of Samir and Gayoto and Lee and so on, that there's a kind of a reflection, I feel, in spirit at least, and perhaps can be made precise, of the giant graviton expansion of the black hole microstates. And I think Samir can tell you more about this, that there are two different ways in which you can organize the black hole index, and one in terms of counting in terms of n equals to 4 Yang-Mills words, the other in terms of computing excitations around giant gravitons. And that it's a mathematical equality of these two indices, which is very non-trivial, but also very interesting. So you do see kind of resonance with those sort of ideas as well. And so you might in general ask, what is this full F-type description for n equals to 4 Yang-Mills? And I'll just put it out there that it's related to the twistor string theory, the A-model twistor string theory, which comes from a holomorphic Chern-Simons theory in twistor space. That is my speculation about the full. And if you want a realization of that is in this paper of Karen Huo, etc., who compute another set of half BPS correlators using this twistor construction. So I've gone over time. Sorry about that, and thank you.
Nice picture of using strapograph to parameterize the modularized space. One brings there's generalization, also the
Supermodularized space.
Yeah.
Yeah, there is, I believe, something. There's a recent paper by Albert Schwartz and someone else, I think, who talk about a similar thing for supermodularized space, but I haven't studied it in detail and see how useful it might be. Supermodularized space is, of course, much more intricate, but yeah, I believe there is something which goes in that direction, and I can only point you to this paper.
Okay, thank you.
In this ADS5 example, you had this open, and closed a few slides ago. One more. Here, that one.
Yeah.
So, do you have you nailed down what this closed string description is? What are these vertex operators?
Yeah, so these would be some Kaluza-Klein modes, but it's only at. I mean, we haven't done a closed string computation which would reproduce that. So in that sense, a lot of this is at this level, but of course these are some BPS objects. So
there must be some coherent state of gravity.
Kaluza-Klein modes on the ADS5, the S5, yeah, but essentially gravitons. Yeah. So maybe there is a way to do it because it's a BPS protected object. You can probably do it in the closed string as well.
Differential in the physics application?
In this, so it depends. So there is a picture behind this, just purely at the level of the two matrix model. There's a dual picture, which I didn't talk about. I talked about in the strings conference, the string math conference, which is related to SL2R mod U1 Kazama-Suzuki model. So it's a little bit of a complicated chain of this thing, which, so basically there is a dual close string, not just the ADS5, but you can just talk about this subsector and talk about a close string that describes just this subsector, which is some topological string, which is this SL2R mod U1 Kazama-Suzuki twisted model. And what one of the things we are doing currently with Matthias and Wei and Edward Zeng is to show that these Feynman diagrams really are giving that, are picking out the points in the moduli space which would, the closed string description essentially picks up these special points on the moduli space associated to these Feynman diagrams. So these Feynman diagrams in a matrix model are discrete Feynman diagrams, and I didn't go into this whole thing. They correspond to integer lengths of the Treble differential. And so these are very special Riemann surfaces, arithmetic Riemann surfaces. And the corresponding maps are a special class called Belly maps. So there you see from the matrix model how to kind of build up the dual string theory in, at least for this subsector, in a very explicit way, using this Treble parametrization. Because they correspond, the Treble parametrization gives you special lattice points on moduli space, and those lattice points are the only ones which admit these holomorphic maps that we believe the topological string localizes to.
And for this lens, so does it have a geometric meaning, geodesic lens between 2 points on the Riemann surface?
Yes, with a special gauge. So there is a natural gauge that you can associate, a worldsheet gauge you can associate to this Treble differential, a conformally flat metric, which is like basically mod phi. And those lengths are basically the lengths in that metric. And yeah.
It's a lens between 2 special points.
The zeros, 2 different zeros of the Treble differential.
What's the geometric meaning of these 2 zeros for the Riemann surface?
For the Riemann surface,
Yeah.
For the Treble differential, these are special zeros.
Yes.
For a given point on the moduli space, you'll have zeros somewhere. I don't know in what way you want to understand what is special about. There is a canonical
Parametrization.
Treble differential, and for each one, there's a special set of zeros. Yeah.
If you go back to the first example that you had,
Kontsevich.
So as you were reminding us, this Kontsevich argument, it has to do with this kind of what you call this F type having a direct interpretation as the integral. That integral looks directly like some integral over moduli space. Is the same true of this other one?
So when you say,
So I understood that you can relate in that first example. I understood you have by formulas, you can relate the 2 open things.
This one, yeah.
By some formulas, but those formulas didn't have as far as I understood, direct interpretation on the moduli space.
Yeah, not directly, yes.
And you also have a direct interpretation on the moduli space relating this thing and the closed.
Correct.
But what about this first arrow? Is there a direct interpretation
from here to here?
Yeah.
So from here to here, the conventional interpretation was not very direct. It was just a statement that the double scaling limit will reproduce, which was which was at the heart of Witten's conjecture. That's why Witten conjectured that these things are computed by this matrix model, and this obeys that KdV hierarchy equation. So it's at that level. These obey the KdV equation, and that's what the generating function of these psi classes obey. So it's at but you would now expect to be able to, so in terms of the Feynman diagrams, you can, if you now think in terms of the Treble lengths, I think there would be a natural description in terms of the dual graphs to the treble graphs. So that should probably have a mathematical formulation, which I don't know how to kind of precisely make. But yes, because these are basically graph duals, there should be a way to write that in terms of these directly.